Right. Then let's move to bias variance. This is a theoretical concept. This is not a model. So I think we have discussed what is bias and variance. So can anyone tell me what is bias and variance? All right. I think we've not discussed bias and variance. So bias is basically let's talk about prediction. Then we'll come to bias and variance. So let's say the data is very complicated, right? This is the kind of data that we are getting. So this does not follow a very simple linear pattern. Here it is increasing and here it is decreasing, right? So this is the kind of data that we are getting. This is the kind of line that will fit the data. This is not a the linear line. A linear line would not a straight line would not capture the complexity. This would be like this. And if you notice that this line captures very little complexity, right? This is not the best way to fit the data. So this line here is more of a polynomial kind of a thing, right? Which means that there will be x1 squared, then there'll be x2 squared or x3 cubed. This is a polynomial basically. So where do bias and variance come in? Now, when we have simplified the model, which means that the data was not linearly related. The data was not linearly distributed, but we have simply used a straight line to fit the data. That is where the data would have high bias, right? We have oversimplified the model. It is an error introduced in the model due to oversimplification of the algorithm used. What is variance? Variance is essentially the opposite. Now, suppose the model is really complex. I mean, the model is okay. It's medium complex. It's of medium complexity, right? This is again the same model that I plotted above. This is the kind of line that will fit here. Now, this line I think can be captured using x squared only. X squared is sufficient to capture this kind of a complexity. That's my understanding. Suppose we have used x1 to the power 4 and we've used very complicated features. These are known as features. So we've used x1 raised to power 4 plus x2 cube, um, x3 also something squared or something, then x4 to the 10th power, something like that. So in that case, this model was not very complex. We could have captured the complexity simply using an x squared kind of a graph. I think uh, this would be something like 2x squared plus 10 kind of a thing, plus 3 kind of a thing, right? If this is 3 and all. I know you all have some familiarity with graphs. You've studied graphs in 11th and 12th in a lot of detail, but this is the kind of graph that we'll get here. But we have tried to fit the graph using this kind of a complexity. In that case, the variance is very high. So the variance is the error introduced in the model due to a too complex algorithm. This algorithm that we have used is very complex. I think this can be something like that this algorithm might be polynomial regression. So just giving an example there. Uh, so there is in this case there is overfitting. Now this is correct. This should be overfitting here. I'll correct that. But bias can lead to underfitting, which means we are not fitting it properly. We are underfitting it. This is the graph for bias, right? I have used a linear model, but I should have used a more complex model. So this is underfitting, and variance can lead to overfitting. Now, what does overfitting mean? Again, we are trying to um, predict something, or we are trying to fit the data in a very complicated model. The data is not very complicated. The trend is not very complicated, but we are trying to fit it in a very complicated kind of a model. And in this case, the training set, now there's a difference between training set and testing set. Please tell me if anyone knows the difference. I think we have discussed this before. If there's if anyone would like to volunteer to explain the difference between a training set and a testing set, this will help us to understand overfitting in a better manner. Right. So the difference between training set and testing set is that the data that we are using to train the model is the training set, and the data that we are using to test the model is the testing set. It's that simple. And the testing set that we are trying to use, it helps us measure it helps us evaluate the accuracy of the model, or how well the model is predicting or classifying, how well the model is working. So that is the training set. I think I have a stable internet connection now. So I was trying to explain training set and a testing set. So this model, this complicated model might give me very good results on the training set, but it might fail on the testing set. So what do I mean by this? Let me go to some empty space. So if you see, right, this is the kind of model that we have. This is a very simple model. This is not a complicated model. But we have used this kind of a function, this kind of a complex function to fit this data that is there in this, to fit the data that we have. Now this data is the training set basically. This is the data that has been given to us and that we are using to train the model. But what about the testing set? Now the testing set would again be something like this, right? The distribution would remain the same. But this kind of a model would not predict well on this kind of a complicated model, would not predict well on this data. It might predict something like this because it is overly complex, and it is essentially matching the training set. It is more designed according to the training set. So it is not predicting well on the testing set. That is basically that is what is called overfitting. So we are overfitting the data. The model fit well on on the training set, but on the testing set, which is this one, this is training set TR, and this is testing set. The model fit very well on the training set, but it did not fit very well on the testing set. So that is bias variance trade-off. So there is a trade-off. You need to balance between underfitting and overfitting. Just need to have the exact kind of a model, which is not even underfitting and which is also not overfitting. So what do we have here? All these 3 points are again frequently asked in interviews. If we do not make the model sufficiently complex, so linear regression is a very simple model. So if we don't make the model sufficiently complex, then it will not even fit on the training set, which is basically the data that we are using to train the model. And this will lead to underfitting, which is high bias. Then as we increase the complexity of the model, the error reduces. But so it reduces first and then again starts increasing. So the error reduces, but only up to a certain point. And this is the graph that shows this. So this is the total error, the black line. This black line is the total error. And this is the bias. So here we have high bias. This is actually bias squared. So bias can be negative also. So we use bias squared. And this is the variance. And here we have high variance. So we need to have a proper, there's a trade-off between variance and bias. So we need to have a proper fit, which means that we want that both of them should be minimum in order for the total error to be minimum, right? And as we continue to make our model more and more complex, we end up overfitting the model, and the model will start suffering from high variance. So in every interview of machine learning, data science, I mean, this is a very common question. In 1 out of 2 interviews, you'll find any question related to bias and variance. All right. Any questions around bias and variance? We'll deal with PCA later on. right? This is again a machine learning model. First, let's understand these things: accuracy, precision, recall, and F1 score. So I want you people to tell me the meaning of each of these from your basic understanding. So can you tell me the meaning of accuracy in case of a machine learning model? I want people to speak up. Any thoughts, any ideas about accuracy? Okay. Anything about precision, recall, or F1 score? You guys can hear me, right?
Yes. Yes, sir.
So anything about these four terms that you've heard before? All right. If not, then we'll discuss. So accuracy is basically, it's a very direct, very implicit kind of term. We are trying to identify how well the model is predicting. What is the accuracy of the model, right? It is the number of correct predictions over the total number of predictions. Very, very obvious and totally understandable, right? And what is precision then next? This means how precise we are, how precise our answer is. Now, if the model predicted something, if the model told us that, let's say this passenger survived, there was, let's say, a plane crash, and we are trying to understand how many passengers survived and how many passengers did not survive. So in this kind of a scenario, we'll feed the data to the model, and we'll ask the model, did this passenger survive? Now there would of course be a lot of parameters on which the model is trying to tell you the answer, right? So basically, precision is the term that helps you understand how precise your prediction was, right? So out of all the passengers that were labeled as survived by the model, right, how many did actually survive? How precise is the answer, basically? And you can see this from the formula also. It is the ratio of correctly predicted positive observations to the total predicted positive observations, which means that there would be some true positives, there would be some false positives also. So this is the total number of predictions that were classified as positive, which means that in this case that the passengers that survived, yeah, out of the passengers that survived, basically. So that is the total number. Then out of this, how many were actually, we know the truth also, right? That how many actually survived. So we'll have TP by TP plus FP. FP is false positives, TP is true positive. And we have discussed TP, TN, all of this before also in statistics. So if you notice, I'm again and again referring to a lot of concepts in statistics. Machine learning is wholly dependent, largely dependent on stats and probability. A lot of models are simply, statistical models. For example, linear regression. We've discussed linear regression, right? This is more of a statistical model. This is statistics. Linear regression was there even before machine learning got introduced as a concept to the world. So linear regression is stats, basically, and machine learning is building on the models, or machine learning is building on statistical concepts. So this is precision. Similarly, what is recall? Out of all the passengers that truly survived, how many did we label as survived? This is recall. And we'll get this from the ratio of correctly predicted positive observations to all the positive observations that were predicted as yes, or that were predicted to be positive. Now, there's a very subtle difference between precision and recall. In the denominator, we are just replacing false positives by false negatives. These are all the people that were actually positive, right? False negatives means that it was a false negative, which means that it was actually a positive, but we have labeled it as a negative. So this is the total number of items or the people that we have predicted as positives. And out of them, this is the true positive number. How many are true positives? How many we have predicted as true positives, basically. This is recall. Now, these are two separate metrics, right, to understand how well the model is performing. And some metric might be more helpful in some case. For example, in the airplane crash model, this kind of a scenario, I think precision would probably a better metric. Probably recall also depends on the use case. But in some cases, this is a better metric. In some cases, recall is a better metric. And there's always a dilemma as to which one we should identify. So what these mathematicians or rather statisticians did was that they created a metric that incorporates both these values, which is known as the F1 score. And it is nothing but the weighted average of precision and recall, right? This is the formula for F1 score. And I always use this. I mean, not always, but mostly I use this in my machine learning models. This score takes both false positives and false negatives into account. False positives from precision, this thing in the denominator, false negatives from recall here. So F1 is usually most useful than accuracy, and it also strikes a balance between precision and recall. So this is kind of a comprehensive metric which helps you utilize the variation captured by both precision and recall. That is F1 score. Now I think we can now discuss PCA. This is again, PCA is another model. Are there any questions till now? All right. So PCA is basically a model which is useful for reducing the dimensions. What do I mean by reducing the dimensions? So let's say I have about 10 dimensions, and my machine learning model can is not very complicated. It can take only 2 dimensions. Let's say I want to use linear regression, right? Let's say I just want to use linear regression, and this takes into account only one dimension, which is this x. On the other hand, a polynomial regression or a logistic regression might be more complicated. They might require more dimensions. But let's say I just want to use a very simple model like linear regression, and I have many features. Now, what can I do? I can reduce the number of features that I have. I can reduce the number of dimensions that I have. So basically, PCA is a model which helps us do that. It is an unsupervised learning algorithm, which means that we don't have the labels corresponding to the data points. It is an unsupervised learning algorithm used for projecting data from a higher dimensional space to a lower dimensional space, which means that let's say earlier we have 3 dimensions, we have everything in 3D, we want to move to let's say 1D. This kind of a task PCA helps us do. I showed you the example of a Star Wars movie uh, way back, I think in my second or third session, right? Let's say we have a complicated algorithm there, or let's talk about an image. I think that will give you a better picture. So let's say we have a 3D image kind of a thing, and we don't want to no, we don't want that kind of a complexity. We just want a very simple 1D straight line kind of a representation of that image. Then we'll probably use this kind of a PCA model. So the newer features, which is the reduced feature. So we won't cut down any feature, right? Let's say I have 3 features. First one is age of a person. Uh, what can be other features of a student database? I want suggestions from your end. So let's talk about a student database, let's say. Age can be one feature. Gender can be another feature. What can be more features here? Um, I'm looking forward to more similar features. Please tell me. So there can be many other features like let's say the marks might not be able to best describe the person. So I think age, gender, and then we probably would have the height of a person or the weight, right, or the physical appearance. These kinds of features. Now let's say I have height. So age, gender, and height. I have three features, but I don't have a very complex model with me. I have a very simple model, and basically I want to reduce these three dimensions to only one dimension. Now what will I do? I'll not simply strike off any of these features, right? I'll probably combine all three features to give me one good feature, right? That is the kind of thing that I'll do. So the newer feature will try to capture as much variance as possible. This is the meaning of the line. I'll basically uh, build a feature. I'll find out a feature which captures as much variance as possible, which captures, which fits the data the best in the best possible manner. The principal components are normalized and orthogonal. This is again a mathematical thing. The appropriate number of components. Now, how do we find out how many components is appropriate, right? How do we find out that whether I want to whether I can turn this 3D model into a 2D kind of a situation or a 1D situation? So this 1 or 2D or something, this will the elbow method will help me identify what is the number that would be best for capturing the variance, as much variance as possible. So the appropriate number can be found out using the elbow method. And this is PCA is mostly used as a tool in exploratory data analysis. I have one session. I'll be having one session on exploratory data analysis where I'll be also talking about Tableau, Power BI, and R. So it is used as a tool in EDA and predictive modeling. So this is the use of PCA. And I think this image, this graph clearly tells you this was the data that you had, right? X and Y axis, simple data. And this is the kind of line that we are fitting. So this is one dimension, this one, and this is the other dimension. So earlier, so basically we have many iterations. And if you notice that after a good number of iterations, the line is stabilizing here, which means that this is the line which helps me identify the best fit for the data. This line fits the data the best, basically. And again, here, these are principal components. PC is principal component, which are the reduced features or the newer features, right? This one, the feature that you get after combining age, gender, and height, that is principal component. So let's say we had this three-dimensional space, right? We had three dimensions initially, and I used PCA to find out two components or two dimensions which are helping me to capture as much variance as possible. So these are the two dimensions that we get here. So I've reduced the 3D space to a two-dimensional space now. And now when I plot these two dimensions, right, on a 2D plot, it will look like this. So this data, when projected on a 2D plot, will look like this. I am very much able to relate to this because I've studied all of this in 11th and 12th. I'm very sure all of you have also studied. So, so I think you will be able to relate. We had studied projections from 3D to 2D, and we also, I think, there are in coordinate geometry or in other chapters we have studied this kind of stuff. So this is very similar to all of that. Right. Before moving to the next algorithm, I would pause here to uh, I'll pause here to ask for questions if there are any. Right. Before I move forward, also please tell me the difference between supervised and unsupervised learning, because that is the essence of our later discussion also. So I've in every slide I've mentioned whether the algorithm is supervised or unsupervised. This is a classification algorithm, logistic regression. Linear regression is again is a prediction algorithm. This is supervised. And then we have PCA is again unsupervised. K-means class. So what is the meaning? Let's say, let's first understand the meaning. I want everyone to be very clear with the meaning of unsupervised and supervised. Um, I have taught this, I think, a number of times. So I want someone to speak up.
Sir, supervised learning has a feedback mechanism, unsupervised learning doesn't have it.
Okay, that is correct. That is correct. I am looking for one more keyword. So this is this is a difference definitely, but there's one more difference.
So in supervised learning, we teach the machine using the data that is already labeled. All is correct.
Correct, correct. So we have data already labeled with us. That is, in that case, we use supervised learning. But if we don't have the labels of the data or the tags of the data, that is unsupervised learning. So k-means clustering is again a very similar algorithm to, so there are two algorithms that look very similar. One is k-means clustering and second one is KNN, k nearest neighbors. So let's first discuss k-means clustering. So basically, this helps you make clusters, right? Let's say you have this kind of a data, you have this data with you, and you want to identify, let's say you have 100 images. Some of them are apples, some of them are mangoes, and some of them are peaches. Three different kinds of fruits. And there's no limitation as to how many fruits are apples or how many fruits are peaches or mangoes. There can be, 90 apples, 10 peaches, and zero mangoes. That kind of a stuff also is possible. So this is the distribution, let's say, right? And here you'll find that this basically before k-means and after k-means, what does this signify? That k-means helps you classify stuff or group stuff, similar stuff together. So this will be one class. Let's say this is apples. This will be the second class, let's say mangoes. And this will be the third class, let's say peaches. So what does k-means do? It clubs similar things together. And what does means identify here? Mean here. So this means that how are we clubbing this together? We are basically trying to find the mean of this data, right? We are trying to find the mean of this data. And similar stuff will be clubbed into one. I mean, if the mean of all this data is very far from the mean of this data, then these will be two separate classes. So we are segmenting customers. If I take the example of a customer, let's say we have some customer features in terms of their spending, purchase behavior, and we would simply like to understand what kind of a customer it is, whether the person wants to buy expensive stuff or cheap stuff, right? That kind of a thing. And we want to understand their needs. So in that case, we just want to figure out if there are some group of customers, we want to club similar customers together. Let's say these are customers who just want to buy stuff only if there are some offers, right? Flipkart uses this kind of algorithm. Amazon also uses, everyone, all the e-commerce websites use this kind of an algorithm. So basically, they help identify, they help understand the user preferences through this algorithm. So they are trying to understand. Let's say this is one group of customers which just likes to buy some cheap stuff or stuff which has offers on it. And this group of people just likes to buy newly released stuff. Yeah, I mean stuff which has come very recently on the racks. Any kind of group, this can be any kind of group. And this k-means kind of a thing, this k-means algorithm helps us identify or divide the data into two classes, two or more classes, right? And what is the process? So we segment customers into K partitions, and K means clustering. This is basically these are known as clusters, and this is based on the closest mean, right? What is the process? The process is first we assign, then we update. So first we find the distance of a target point from all the clusters and assign it to the cluster with the nearest distance. Now this you'll find the formula for this also. There's a mathematical explanation to this, that we are trying to find the distance of each point from the mean, right? And if the distance is less than some particular value, then we'll assign it to the same cluster. Now let's say this is the point, this is a data point, and this data distribution has this mean, and this data distribution has this kind of a mean. This red one is the mean here. So which group will this data point go in? Basically, how will we find that? We'll calculate the distance of this point from the mean, and we'll calculate the distance of this point from this mean also. Whichever is the least, it will go in that group, right? So that is the assignment step. Then we update the cluster centers, which means that after we get this one, let's say in this class, in this group or cluster, then we'll update the mean. And then we'll repeat this for all the other data points. Let's say we have this data point, many other data points. That is the process here. There are two main types of clustering, flat and hierarchical. This is theoretical. Right, this is the process. So basically let's wait for this to start from the beginning. Yeah. So earlier we had this kind of a distribution, and as the algorithm runs, it is dividing more and more data points into different classes. And at the end, it has clearly identified that this is one distinct class. This is one distinct class, and this is one distinct class. This is the mean of this class, this is the mean of this class, black one, and this is the mean of this class. So we have been able to understand the classes. We have been able to clearly identify the clusters, right? This is again a similar thing. The iteration is basically for how many times we are running the model. So that is the iteration. And earlier it looked like this, but then the means kept on adjusting. The mean kept on adjusting itself, and then this was the final result that we got. These are four distinct clusters, right? I think this is before we start K nearest neighbors. I think we've covered about 5 algorithms today, 4 or 5, and next I'll cover K nearest neighbors. We have 3 models pending. First one is K nearest neighbors. Then we have support vector machines, and yeah, these are the only 2 models that we have left. So we'll first cover both of these models in the next class, and then we'll start with SQL and Google Analytics. So we'll again move back to data analytics. I don't want to go into more depth within machine learning or within data science, because this might become very much mathematical and very much statistical. So you just need to know the concept behind each of these algorithms, and just need to memorize this graph basically, or this GIF. You just need to understand the working of each algorithm. So I think with that, I will end the session, and as I've already told you, we'll cover Google Analytics and more machine learning. Now I want you to read more about machine learning from either Towards Data Science blogs or Medium. And there are other communities also, like Analytics Vidya. If you want to do a competition, you can go to Kaggle also. So these are some places to explore more about machine learning. And like I've already told you before also, you should probably go ahead and do a machine learning course. I discussed this in the last session also. these are some courses that we discussed last time, right? So you can take up a college course. These are some of my personal recommendations within machine learning. So you can go ahead and do these. These are the ones that I also did. So I think if you just do this course alone, the Udemy one, this should make you ready to attack any algorithm or any kind of problem statement. And you should probably be able to also participate in case study competitions or even your placement process after this. So that is a good course. Then Python and SQL courses are, so SQL is not related to machine learning in any manner, but Python, you should at least have some basic idea of Python before starting machine learning. Python or any similar language used in ML. Then of course you can take up projects, and these are some places where you can take up projects. Python, MATLAB, and R are three languages that are very commonly used in machine learning. Python is most commonly used. And then, yeah, this is it for this session.